really a great pleasure to be back in person and give such a presentation. Thanks a lot for the opportunity. Most of you don't know me, so a quick summary. I grew up in Switzerland, close by, speaking French and German. Then I came to EPFL. I did my bachelor master's in the material science department, joined NPAR for a short stay. Then I went to IBM Research, where I spent most of my last 5 years doing simultaneously mental the University of Cambridge and a PhD at the University of Bern. And now I'm back here at EPFL, and it's really a pleasure to be here. And also part of the NCCR catalysis project in Switzerland. Today, I will talk to you about accelerating synthesis with transformers, and we'll first go through data representation models. Then I will show you how the models I developed in the last few years are implemented in the reaction for chemistry ecosystem, some more explainability and interpretability of the models, and then an outlook and questions. You probably all know that we have a nearly endless chemical space to explore. And if we take drug-like molecules as an example, then the estimated number of possible drug-like molecules is 10 to the power of 60. And how can we go about designing new molecules? The question that we can ask ourselves is, what molecule do we want to make? And we have a lot of property prediction models, inverse design models, but what is typically missing in the machine learning papers is the experimental validation. And one reason for that is that it's not that simple to synthesize molecules. And this was my main focus for the last few years, how to accelerate chemical synthesis using machine learning, pushing towards experimental validation. If we look at a typical chemical reaction from the literature, you might recognize those figures from your chemistry courses. Then we can do several machine learning tasks. Maybe for those of you that are not in chemistry, you have on one side the reactions. Those are the agents, and this is the product of the reaction. And one task that we can approach in machine learning is to predict the most likely product, and this is the forward reaction prediction task. Another task is to say, okay, I have this product here, but I would like to get the precursors, the molecules that can form bonds to make this product here. And this is the single-step retrosynthesis. But as you might have imagined, molecules are typically not made in one step. And that's why there's a more challenging task, which is multi-step retrosynthesis, where we want to resolve a synthesis route to commercially available building blocks. And then there are tons of classification and regression tasks, for example, predicting a specific yield of a reaction or trying to classify it into a name reaction. And this is maybe a bit more obscure, and I will come back to that. It's atom mapping. It's trying to find the correspondence between product atoms and reactant atoms. What we need to approach any of those tasks is chemical reaction data. And there we have patent databases that are open and freely accessible. They were text mined from the patent. So there was a huge work in the past to analyze such synthesis procedures and mine the different components that take part of the reactions and make them accessible in a machine actionable form. Then we have literature reaction databases. They cover broader space of chemistry, but typically they're not freely accessible. So it's it's really hard to get access to them. And even if the quality is higher, usually we go back to patent reactions to showcase our models. We can also imagine, okay, ELN is electronic lab notebooks, so data that was collected by an experimental chemist in the lab by typing in all the components of the reactions, or HTE is high throughput experimentation. It's robotic platforms on which we run a lot of chemical reactions with slightly different conditions, and then we can automatically generate data. But those typically cover very small chemical space but provide higher quality data at the same time. And we can augment all this with simulations and compute some descriptors with quantum mechanics. Most of my talk will focus on patent data because it's pretty accessible, and there I'm really thankful to Daniel Lau and Roger Sale from Next Move Software, who first, Daniel in his PhD thesis, he text mined the US patents, and then when he was at Next Move Software, they made available a larger data set of chemical reactions. And one representation of such reactions and molecules are smiles. This is the reaction smiles, and here we have the corresponding 2D depiction. And if you see, the dots are basically the separation between the molecules, and the two greater signs that you see here represent the reaction arrow. I already mentioned it, atom mapping. Atom mapping is when you have the correspondence between the product atom and you know exactly what it was in the reactants. Once we have like those chemical reactions, we can represent them, as I said, in this text-based format. And then after atom mapping, we can further analyze those chemical reactions and, for example, extract the reaction template that describes the core changes that are happening in this chemical reaction, or represent the whole reaction as a condensed graph of reaction CGO. Well, typically correct, the atom maps that are required to get those more advanced representation of the reactions are typically, wrong in many cases in the open source data. And this was a warning from the dataset creator. And this is why I try to develop methods that are atom mapping independent in the first stage. I've already mentioned smiles. This is just a quick recap. It's a line notation for molecular graphs that was developed in the 80s. And you can, maybe let's go back here. You can follow the string here. Brackets are for branching, and you can open rings and closed rings with numbers. And basically the color gives you the corresponding atoms here in this molecular graph. There are several problems. You can generate invalid smiles. There are not enough semantic constraints. They're not unique, which sometimes is a disadvantage, but sometimes can also be used as an advantage. By not unique, I mean that one molecular graph can have several different smiles that correspond to that graph. And we will see this later during my talk. I've used smiles as a representation because it basically allows me to represent atoms as letters and molecules as words. And then after splitting them, tokenizing them into sequences of atoms, I can borrow methods from natural language processing and directly apply them to chemistry. The basic example is forward reaction prediction, where we try to predict the most likely product given the precursors. And this can be cast into a sequence-to-sequence translation process, where you have an encoder on one side that encodes the input, computes the most interesting features, and on the other side, you have a decoder. I think for this audience, I don't have to like explain this in more detail, but yeah, those early sequence-to-sequence models had one problem. This was the fixed size vector in the middle, and people in natural language processing came up with this attention mechanism. And what is different here is that every single atom or word or token is individually encoded by the encoder, and at decoding time, the decoder gets access to this memory bank and can query through this attention mechanism the most important information. In 2017, we then had the transformer architecture published by Google. The two key changes was that instead of recurrent neural networks, only the stacks of attention layers were used, and they also had this multi-head attention that facilitated the focus on multiple tokens simultaneously. Back then, we quickly adapted this to chemical reaction prediction, and without showing or integrating any rules or much chemical knowledge, just by seeing millions of examples of correct chemical reactions, this model could outperform all the reaction prediction models and accurately predict unseen reactions. This is a standard benchmark. It's not the best one. It doesn't contain any stereochemistry, but those were the results back then. And there was some catching up later on, but it performed quite well back in 2018 and stayed on top of this benchmark for more than 2 years. This is also a kind of fun exercise. It's a human prediction benchmark. Basically, a group at MIT gave 80 reactions that were separated in different bins, from very frequent reaction samples to rare reaction samples. And they gave those 11 chemists the task to like predict the most likely outcome. And this is how the average human performed their model. The best human, which was the professor at MIT, and back then our molecular transform. In the meantime, just to conclude this reaction prediction on those data, this typical benchmark data set, there were a lot of improvements, and just to show you what led to those improvements, it was as expected somehow from the development we had in natural language processing, extensive data augmentation. So this is what I was hinting to before, that for one single molecule, you can have a lot of different smiles that represent the same molecule. You can, in chemical reactions, also rotate all the components and yeah, like that, extend your data. Other improvements were based on large-scale pre-training, where encoder and decoder were first trained on molecular structure before being fine-tuned on chemical reaction prediction tasks. And I really also like this work here from Commun, where they used the graph encoder, but then transformer decoder. So they went from graph to text and had more or less the best of both worlds. When I transitioned to the University of Bern, we went into a different direction. We asked the question, yeah, what is really missing in those typical benchmark data sets? And one was stereochemistry. Stereochemistry is that it's basically that you can have two mirror images, like your left and right hand of the same molecule. And it's hard to describe this in a graph. And it can be represented to a certain extent with smiles. So we we focused on reactions with a lot of stereoselective. And we focused in this publication on carbohydrate reactions, and those compared to pattern reaction dataset where you have less than one stereocenter on average in the product. It had on average 6 stereocenters. So 6 of those are like bizarre left and right stereocenters in the product molecule. And to actually predict this product, the model had really to capture this stereochemistry. And also the other thing was missing is experimental validation. And for that, I teamed up with Giorgio that you see here on the right. He performed the 14-step synthesis of a lipid-linked oligosaccharide. And using transfer learning, we saw huge accuracy boosts on all test sets, like the test set that was close to the reactions, the carbohydrate training reactions, literature extracted reaction data set, and also the experimental formed reactions. Here is just one example, cherry-picked from a reaction in the test set, and the JAX test set. And if you look at this, the atom mapping is kind of obvious. You immediately see that the product corresponds to those 2 molecules here. But even for a human expert, it would be very difficult to say if this bond is formed on axial or equatorial position, and whether it would form an alpha or beta bond. So you have 4 different possibilities, and a carbohydrate expert would have difficulties to predict that, and the model learned it from the data we collected. And this transfer learning approach, in the end, is really applicable to any reaction subspace of interest. For example, it was recently used for enzymatic reactions. One question there is how to represent the enzyme, and in those transform models, we can easily also take a human description of an enzyme and condition the prediction on that. And this is work by David Crater from the Reymond group. And there's also an alternative representation called EC numbers that Daniel Prof, who is now a postdoc here at EPFL, used to also approach those enzymatic reactions, like biocatalyzed transformation. But with this, I will stop on the forward reaction prediction task and move on to an even more challenging task, which is retrosynthesis. In retrosynthesis, we have a target molecule, and when we want to find a commercially available building blocks and that are put together, going backwards, like you see here, step by step, until we know the whole synthesis that we need to construct the target molecule. And there were multiple approaches for multi-step synthesis planning in the past. There's great work by the group of Grybowski et al., who collected 10,000s of different reaction rules over a time of 20 years and tried to make an expert rule-based system augmented with machine learning. There's a very famous Nature paper by Segler and Waller, who automatically extracted rules from the atom mapping and then used the Monte Carlo research, which then inspired work at MIT and AstraZeneca. We made a similar version of this synthesis planning tool, but openly accessible. And at IBM Research, we made this reaction for chemistry platform, which has some key differences to the other approaches in the literature. Yeah, we focus on those template pre and atom mapping independent models. There are tons of startups and proprietary tools also doing very similar tasks. But in the end, it often boils down to having a single step prediction approach that predicts like the precursors given the target molecule. They can be template-based, graph-based, smice-based, whatever, and the search algorithm, which is on top, and that combines those single-step predictions. On the next few slides, I will focus on the one I was involved in, which we did in a collaboration between IBM Research and the University of Pisa. And this, we used, kind of obvious probably now, we used two different molecular transforming models. One to go backwards, so given one molecule, predict the precursors, and then ideally this model can predict tons of suggestions, and ideally you would show them to an expert chemist who would say, okay, this one could work, this one could work, this doesn't work at all, and then don't try this. But this is just too resource intensive, and because we didn't have access to that, we took our best artificial organic chemist, and this was a forward prediction model. And what you can do there is just by fixing the target molecule and showing those pairs of suggestions plus the desired target molecule, you can just compute the likelihood of this, or the score the model would have given to this pair. And like that, we use this score to like store different roots in the tree and find promising results. What we do differently compared to other approaches in retrosynthesis is that in the single step, we not only predict reactants, we also predict reagents, catalysts, solvents, everything at the same time. And this is something that is hard to do with just a simple template-based approach. What we always want to evaluate our machine learning models is to have some kind of adoption by the people that can actually benefit from them. And at IBM, we had this reaction for chemistry platform. If you're interested, you can check it out. There's an online platform that looks like this or looked like this at some point. Maybe there are some visual changes recently. But there, the chemist can simply draw molecules, click on the run prediction button, and get back predictions with the confidence score. And also the retrosynthesis interface is available. And it's really nice because there's also an interactive, there's the fully automatic retrosynthesis on one side, but also an interactive mode where the different suggestions can be rated by and selected by the human expert. And so like that, retrosynthesis almost becomes like a human AI interaction. Just to have some feedback that we got back in 2019 to convince you that this could actually be used somewhere in a lab.
Hello, my name is Alessandro Castrogiovanni from University of Basel, and today I want to show you how I use IBM Reaction for my everyday research. And I selected for you a molecule to synthesize, and the program is giving me the retrosynthetic pathway, the most convenient retrosynthetic pathway. And for example, in the case of this ketone, the program is telling me how to prepare it with halogen metal exchange, and then addition of the lithiated species to the acid chloride, and then the protection of the ether with pyridinium chloride to deliver the product. But this is not just the only result. There are other outputs given by the program, and I would show you another one. In this case, they do the halogen metal exchange on another substrate, and then they perform the oxidation with manganese dioxide and deprotect. And in my opinion, everything makes sense, and it is helping me and my colleagues to achieve the substrates, the synthesis of every substrate.
Yeah, so it's kind of fascinating that actual some syntheses that are automatically predicted make actually sense, even if they are predicted step by step and learned only on single step reactions. So what is next? So at IBM Research, definitely robots, because imagine you're a chemist at home, you do the design of this molecule, then you connect to the cloud, you get access to a synthesis planning tool, and then another tool that converts those different synthesis steps into sequences of actions that you could then run yourself in the lab. But if you have access to an automatic platform, you can also, and all the ingredients are available, you can also run the synthesis directly on the platform. And let me just point to Theodore Laino and the RoboRxN team. This was a huge collaborative effort to make this whole pipeline. This here is just an example of this platform running running for synthesis of a photo acid generator that was predicted by the retrosynthesis. So at IBM Research in Zurich, you have such a prototype of this robotic synthesis platform. What is at the core of this is also the prediction of the actual synthesis procedure. And this work mainly led by Alain Rocher, where he trained models that can convert those reaction smiles into actions, including reaction conditions that give them a first suggestion how a specific chemical reaction could be run in the lab or by the robotic platform. It's really useful to have those standardized actions predicted. In the first part of my presentation, okay, I took a bit longer than expected. Yes, we looked at sequence-to-sequence transformer models for reaction prediction, retrosynthesis, and also the action prediction model was based on a sequence-to-sequence transformer. In the second part, we will have a quick look at encoder-only models that take the whole chemical reaction as an input, and then we can use them either for reaction classification or yield prediction, the regression task. So you're all aware of what the transformer model looks like with stacks of self-attention layers. What it gets as an input are those tokenized reaction smiles. Then we have those multiple heads that can all learn different functionalities to learn better and better contextual representations of those atoms. And in the end, we can fine-tune this model on a regression or classification task. The training typically happens in two stages. First, the pre-training stage, and there we were really not creative at all. It's just a mask language modeling task where we randomly mask different tokens and we let the model predict the mask tokens. And because you cannot replace any atom with any other atom, the model has to capture some kind of chemistry to perform well in this task. Then one example downstream application is reaction classification, and for chemists, those reactions would have a clear structure, and a lot of the reactions have been given names, and we used a database that had reactions and the named reaction classes, and by training a model on that, we could show that those models were accurate. But what is more exciting for me than the accuracy on the classification task is that when we chop away the last layer, the head of the transformer, we could get back data-driven fingerprints. And those fingerprints allowed us to map chemical reaction space. The quality is probably better on Zoom than here on this projector, but yeah, this also based the two-dimensionality, the 2D reduction is based on the TMAP algorithm by Daniel Prof. So, yes, here we have such a reaction atlas. In action, we can layer different properties, categorical properties, continuous properties. We can zoom into this atlas. It gives you a bit an overview of what your data set looks like, not only like locally, but also globally. And we extended Daniel's framework to be able to display like chemical reactions and compare nearest neighbors directly. What this can be used for is if we do a prediction of a new chemical reaction, then we can use this fingerprint to query for nearest neighbors, for example, in the training data set. And when we do so, we get access to all the information that was stored with the training reaction. And sometimes this contains also, if you will, as you will see here, those are similar reactions to the one that got predicted. And we can display the synthesis procedure. And like that, the chemist has an initial point to know how the new reaction could actually run in the lab. If you're interested, this is a small tool called Reaction Fingerprint. It's pip installable, and there's open source code online. And some folks at AstraZeneca wrote a reusability report on that and made it work on their internal data. Another task, let's move away from classification, is the prediction of reaction yields. And there, because we had so much experience with the patent data, we tried this first, and long story short, it didn't work at all. There's just too much inconsistency in the local environment. If you have two different chemists in two different labs doing a similar reaction, but measuring it, executing it slightly differently, measuring it with different tools, in the end, they will end up with completely different yields and they're not comparable anymore. So it was really hard to learn trends. What worked better is when we went to high throughput experimentation data, where you have to imagine that you have a controlled robotic platform that executes similar reactions and always under a controlled environment. And there we can, this was work by Aleman et al. From the Doyle group in the US. And we took this data set with 4,000 Buchwald-Hallweg reactions and just asked the question, can the transformer learn those fine-grained differences in the reactions to learn to predict, accurately predict yields? And to our surprise, it actually worked quite well. And if you hear transformer models, usually you think that they are very data intensive. They need a lot of data. And that's why we also went down to smaller and smaller training data sets. And even with 100 points only, we could beat a random forest model that was based on DFTs, so quantum descriptors, so that were calculated with simulations for the different components in the reactions. The obvious question then is, why do transformer work so well in chemistry? And that's when I teamed up with Ben Hoover and Hendrik Strohwald from the IBM MIT lab in Cambridge, and we performed the training of the transformer models on millions of unlabeled smiles, just using this masked language modeling task. And then we inspected the model internals. And we can inspect the attention weights for a given head and layer. And this is a bit confusing at first, but you have the input reaction on top, the input reaction on the bottom, and what we are displaying on the two, between the two lines are the attention weights. And if we look at the specific atom, we see that, for example, here it looks at the nearest neighbor. And we went through several heads and layers until we found such a structure here, such a signal in one of the heads. And if you look closely, the precursor atoms always point to a product atom, and vice versa. The product atoms point to precursor atoms. And if you remember the beginning of my talk, it sounds a bit similar to atom mapping, like the correspondence between reactant and product atoms. And indeed, the transformer models have automatically learned how atoms rearrange in chemical reactions. And we use this to develop Reaction Mapper, which is an open source tool that if you provide it with a not atom mapped reactions, can basically give you back those connections. And this is kind of a hard task to do, and there were several approaches since the 1970s to try to tackle this task. And on an independent benchmark with roughly 1,800 curated reactions, Reaction Mapper was ranked best, even better than commercially available, so, and much better than the open source alternative. But yeah, I can skip this, but we had kind of a nice community response on that paper. It was even featured in a book, and there was a nice quote by an expert in the field, which said the cases where ML seems to work almost like magic are rare, but this is one of them. So, yeah. We can use this tool to map huge reaction data sets, and then once we have the mapping, we can extract more information about the reactions and then use them for downstream applications. For example, in synthesis planning, there are template-based approaches like this famous Nature work and other works from AstraZeneca and from MIT. We have graph neural network approaches, but they extract the ground truth from the atom mapping. And we have those smice to smice approaches that are atom mapping independent. And yeah, if we have better atom mapping in the end, we can improve all those different approaches. So yeah, also here we have open source code available and them online. I don't know, this is probably less interesting for you than for chemists, but it's kind of nice thing to play around. Briefly, before I summarize my talk, I just want, yeah, this is the typical plot in NLP models getting bigger and bigger. We, on the other hand, always decreased the size of our models. We started with a 20 millions per meter transform model, the reaction fingerprint and the reaction mapper went down in size. And everything I've shown you today can be trained on a single GPU within like max 84 hours max. So summary so far is like, you've seen encoder, decoder, transformer for reaction prediction and retrosynthesis, and encoder only transformer for classification, fingerprints, reaction yields, and atom mapping. So what's next is the question. And here it's like there are lots of ideas around how to combine different data sources and make use also of human knowledge to improve those models, go towards the low data regime. And there's also SwissCat Plus currently built at EPFL, which is a fully automated lab, really the lab of the future. And here just to show you some preliminary results from Bojana, who is here today in the room, that she presented at EPFL AI for Science, where she is working on optimizing chemical reactions using Bayesian optimization. So I hope I've been able to convince you that we can apply machine learning in chemistry and in particular for synthesis. If you're interested, there are those reaction fingerprints that are quite useful for chemical reactions as a representation. I think if I have to highlight one single result, it's clearly that we were able to see what the transformer learned on those chemical reactions, and we make use of that signal to build an open source atom mapping tool. And we have, yeah, lots of future projects that are aiming also towards experimental validation, and we have ongoing collaborations with Sept. With this, I would like to thank Theodore, Laino, and Jean-Louis Reymond, who were my supervisors while I was doing most of that work, and also my group. We should definitely do a new group picture now that we have a few more people arriving, but this is from applied machine learning days. And thank you very much for your attention.
This great talk. Thanks to you, the audience, online and on site. Regarding next events, you might have seen it. We have a workshop coming up with Rick and AIP on Wednesday and Thursday this week. You can still sign up. It's in person for those at EPFL. So it's INF1. It's just like at the ground floor of this building. And then next week, 12 September, same place, same time, other professor, Paulo de los Rios, who is going to present his work and his lab. So thanks a lot. See you soon. Bye.